So that should be fine. All right. Now, anyway, as long as you're able to see what I'm writing, it should be okay. I'll try to speak more slowly so that even if the audio is not very smooth, you can still understand what I'm saying. Okay. So if you have the binomial theorem written down, using that, we will be expanding this expression. Okay. So as I already told you, this limit is defined to be E. What we need to do is evaluate it. Okay, so this is just a definition. It does not tell us the value. So to get the value, we need to evaluate this limit somehow. And since it is not, it's not of the form some polynomial upon some other polynomial. It's not of this form. So we have to approach it some other way. And that's why we'll be using the binomial theorem, because it is, if you can see it is very similar in this form. You have A and B here. Okay, these are your A and B, and there is an exponent. So we have to expand this bracket according to this binomial theorem. Only thing is that here it's three different variables A, B, and N, whereas over here it is one of the variables is 1 by n. So that is also a function of n. So this B here in our case is also a function of n, and the exponent is also n. So that doesn't matter. When you are expanding it using binomial theorem, that doesn't matter. So what we'll do here is, right, so consider this limit. And expand it. So what is the first term here in the binomial expansion? You have nc0, so that's just 1, a to the k, or we can also write it as, instead of this, you can write it as a to the n minus k and b to the k, so that doesn't matter. So we'll take a as this. So it is beginning with the highest power of a. So beginning with a to the n. So this will be a to the n plus nc1 a to the n minus 1 b, and so on. Okay. So over here you have 1 to the n plus nc1 1 to the n minus 1, that's still 1, times b to the 1. So b is 1 upon n to the power of 1 plus nc2. Again, since this is 1, it's never going to matter. It'll always be 1 in every term. So we only have to look at the powers of b. So this will now be 1 upon n square. The next you'll have nc3 and 1 by n cubed, and so on. So does everyone follow it till here? Please reply in chat or so. You understand till here? Okay. At any point, if you don't understand what's happening, please ask me. Okay. So now if you remember, second term is b square. No, the first term is nc0 a to the n, b to the power 0. So the second term will be the nc0, a to the n, b to the 0. Okay. Oh yeah, third term is, yes, 1 upon n square, nc2, a to the n minus 2, b square. So yeah, and so on. Okay. Now, remember that we're going to compute nck as not, so normally this is, when you learn the definition, you learn this is n factorial upon k factorial and minus k factorial, right? But remember that we're going to compute it in a different way by expanding this n factorial into n minus 1 down to n minus k plus 1 times n minus k down to 1, but n minus k down to 1, if you multiply, that's n minus k factorial. So that part will get cancelled here, and so you just have this in the numerator, and in the denominator you have k factorial. Okay, this is nck. So if we use this here, this is still 1. Here you have n times 1 by n. I'll cancel it later, but right now I'll just write nc1 is n. nc2 is n times n minus 1 upon 2 times 1 by n square. And similarly, what will be the next one? n minus 1 n minus 2 upon 3 factorial, that's nc3, times 1 upon n cube, and so on. Right. Okay. Now here, as you can see, you can cancel the n. Okay. So this n can be cancelled with this, and you just get 1 upon 1. Although I'll change it later. You get 1 upon 1. I'll write this 1 here because we need to find the pattern here. So I'll not simply write 1, I'll write 1 upon 1. Whereas here what happens? You have a 1 by 2. So let me keep that there, 1 by 2 times one of these n's will get cancelled because there is n square in the sorry, there is an n square in the denominator. So one of these will get cancelled. That will just become 1, and n by n is 1, and the other is n minus 1 by n, right? So it is n by n times n minus 1 by n after the 1 by 2. So this n minus 1 by n is 1 minus 1 by n. So it is 1 by 2 times 1 times 1 minus 1 by n. In the same way, what will this be? You have a 1 by 3 factorial in the denominator. Okay, so in fact this is also 1 by 2 factorial. Okay, it's 2 is 2 factorial, but in order to see the pattern more clearly, I'll write 1 factorial, 2 factorial, 3 factorial. Now what happens over here? One of the n's, which is by itself, it gets cancelled straight off, and this is n minus 1, and then you have another n here, right? You have two n's remaining in the denominator because one of the n's we cancelled, 2 remaining. This n minus 1 upon n can again be written as 1 minus 1 by n. Then you have n minus 2 upon one more remaining n, so that is 1 minus 2 by n. Is this clear? And so the same pattern will be followed throughout. Okay, I hope this is clear. If not, please ask. Now, actually, we are going to evaluate. So this is without the limit. It's just the expansion. Is what divided by n? Okay, wait. Parth, please ask your question in the group itself. Please ask. You're asking if the term is divided by n, but I'm not sure which term you're asking about. The whole term is not divided by n. I'm not sure what you're asking. The individual terms. Yeah, each term is divided by a different power of n. The first term is divided by the 0th power of n. So there is no n anywhere in the first term. Because remember, this is the binomial expansion. So yeah, I'll write the first few terms here in the general case. What you have here is a to the n plus nc0, that is n, a to the n minus 1 b, nc1 rather, this is nc1. Then nc2, so that's nn minus 1 upon 2, a to the n minus 2 b square, and so on. If this a is 1, then so if this a is this is 1, then what happens is all these terms will be just 1. Okay, this will be just 1. So you'll have only the powers of b here. Okay, so in our case, b itself is 1 upon n. Okay, here this is b. In this application of the binomial theorem, this is b. A is 1, b is 1 by n. So the powers of 1 by n are over here. So this is b, b square, b cube, and so on. Is that clear, or are you asking something else? Okay. So that's what. Every term has a 1 by n or 1 by n square or 1 by n to the power k in general in it. And it also has nck in it. So when you have nck, that expands into this, which has k different brackets. So the general term, if I write it, this is the pattern, as you can see very clearly. Still, if you can write the general term over here, that will be this nck, a to the power k is 1, b to the power a to the power n minus k, that's 1, and b to the power k, that is 1 upon n to the power of k. So this nck is n minus 1, etc., n minus k plus 1 upon k factorial, and then you have 1 by n to the power k. So if you look at it, there are k different brackets here. This is the first bracket, which is n minus 0. Second one is n minus 1, and so on. So this is n minus of k minus 1. So if you write it that way, this is n minus of k minus 1, right? So this is the kth bracket. Because the first bracket is n minus 0 in it. So the kth bracket is n minus k minus 1 in it. There are k brackets here, each with one n, and there are also k n's in the denominator. So you can cancel each n here with one bracket, but they don't fully cancel out. So you have this kind of term here, 1 by n or 2 by n and so on. Okay, so you'll have this will become 1 by k factorial, as you can see in each term, and then 1 times 1 minus 1 by n, 1 minus 2 by n, so on, 1 minus k minus 1 by n. Okay, so that's what is happening in each term. This is, as you can see, k minus 1 when it is k factorial here. So when it's 2 factorial, it goes only up to 1 by n. If it's 3 factorial, it goes up to 2 by n and so on. So next will be 1 by 4 factorial, and there'll be 4 brackets going up to 1 minus 4 by n. So fine, this is our binomial expansion part. Now we need to evaluate this as a limit. So as I said, this is only the expansion. So when we apply the limit, what happens is, now n is approaching infinity. Okay. So the first term here has no n in it, so nothing changes, it remains 1. And the same goes with the second term. But in the third term, with the 1 by 2 factorial, what happens? 1 by 2 factorial again is independent of n, so it remains as it is. This is 1, that also remains as it is. Whereas over here you have 1 minus 1 by n. But n is approaching infinity. So as n approaches infinity, 1 by n approaches 0, right? So in every term, 1 by n is going to approach 0. So this bracket also becomes 1. Same thing here. You have 1 by 3 factorial, then 1, then again 1, again 1. It's 2 by n, but that still doesn't matter because 2 by n also approaches 0. So if it is in general k by n, k by n will approach 0 because n is approaching infinity and k is some finite number. Okay. So that means if you have the term of this form, 1 minus k by n, this is approaching 0, so this is approaching 1. That's what happens in every term. So finally, what is this? 1 plus 1 by 1 factorial plus 1 by 2 factorial, then 1 by 3 factorial, and so on. Okay. So this is, if you want to write it in summation notation, this is summation k equals 0 to infinity 1 upon k factorial. Remember that 0 factorial is 1. So the first term will be 1 upon 0 factorial, which is just 1. Second term will be 1 upon 1 factorial. Third will be 1 upon 2 factorial, and so on. Okay, so this is E. This is defined as E. So E is summation k equals 0 to infinity 1 upon k factorial. So this is the first limit we are evaluating, which is not in the polynomial upon polynomial form. Okay. This is the this is called the series expansion of E, or actually this is the definition of C is according to the limit, and this series gives you the value of E. So remember that we did this in the calculator, where we found the value of E approximately by taking this expression and then evaluating it for larger and larger n, and we got some value that approached the value that approached 2.7128 and so on. Okay, how does 1 minus k by n tend to 1, right? Okay. So what we're doing here is n approaches infinity. So if n approaches infinity, what does 1 by n approach? 0. And so if k is a finite number, a fixed number like 2, 3 and so on, in each term k is finite and fixed, right? Only n is approaching infinity. So k upon n also approaches 0. Correct. What about 1 minus k upon n then? So if this approaches 0, this whole thing approaches 1 minus 0, which is 1. Is that clear now? Okay. So right, we evaluated this approximately in the calculator by considering larger and larger values of n. So if you take n equal to 1, you will get 2 to the power of 1, which is 2. If you take n equal to 2, you will get 1.5 to the power of 2. So that's 2.25, right, and so on. So if you go to larger and larger values of n, you are getting something close to 2.7, 2.7128 something. So you can also get that from this series. So if you take, obviously this is an infinite series, so you cannot actually find the sum without some summation techniques, but then if you do it, you will just get E as the answer. There is no other answer for this. However, when you have the infinite series, what you can do is truncate it to a certain finite number of terms, which truncate means you take the sum up to a few terms and then stop. So if you take only 1 plus 1 by 1 factorial, how much is this? This is 2. Now if you take one further term, so that's 1 plus 1 by 2 factorial, right? So 1 by 2 factorial is 0.5. So if you evaluate it till here, you get 2.5. And you can further take 1 by 3 factorial. 1 by 3 factorial is 1 by 6. So 1 by 6 is how much? 0.18 something, right? I'll have to use a calculator for this. One by 6 is 0.16. Yeah, okay. So this will be approximately 0.16 or 17. So if you add third term, you get 2.67. Okay, and then you can further add 1 by 4 factorial, which is 1 by 24. Which is 0.041. So if you further add 1 by 4 factorial, you'll get 0.041 to 2.71 approximately. Okay. So you can see that even from the series, you can see the value approaching that value which we got using the other method. But the difference is that this series gives you the exact value. And if you could evaluate it, or if you want to evaluate it to a certain level of accuracy, you can take as many terms as you want and get the correct value. And anyway, even if you're not computing the value in decimal form, this series itself is the value. It's not in decimal form, it's in some series form, but it is the value. So this is the exact value. Whereas with the calculator, what we did, that does not give you the correct value at any point. Right? And you cannot justify it theoretically that what you're getting is indeed approaching some value that you claim. So this method, although it is theoretical, gives us the exact answer in some form. Let's say in the best form possible in this case. Normally, if you can get an exact decimal expansion of it, that is the best form possible for practical purposes. But that's impossible in this case because E is actually an irrational number. So being an irrational number, it does not have an finite or recurring expansion. Okay, so you have the series is the best form that you can get. All right. So the importance of E is not its value as such. But as we'll see in differentiation, it also gives rise to an important function. Okay, so just a minute. Okay. So let me rewrite that here. What we have defined is E is defined to be this limit. Which is sorry, Parth, you're asking some question. Okay. Yes. Someone is having the mic on, I guess. If you need to ask a question, you can. Otherwise, please mute that. Let me see. Okay. So you're asking if we need k equal to 0, so the value should decrease. No, k equal to 0 gives you the first term only. This is an expansion, so this is a summation, right? So when you expand this, you will set k equal to 0 to get the first term, but then k equal to 1 to get the second term and so on. So all the terms are there. And you can see that these are all positive numbers. So as you add more terms here, as in when you evaluate this summation to larger and larger number of terms, you'll always get a larger value. However, this is a so-called convergent series. So that means the value itself does not approach infinity. The value is finite. It does not approach infinity. But that seeing why that is so requires some other theory which we are not going to learn. So for now, roughly you can see that it is probably finite by evaluating it to larger terms and seeing that the value does not increase, never increases beyond 3. Okay, so it's actually 2.71 something. You can see that no matter how many terms you add, the value is never going to cross 3. So that tells you, although not fully rigorous, that does tell you that probably the sum is finite. And in fact it is. You can prove using some other techniques that the sum is going to be finite. But yeah, it is not decreasing. It will always increase because all the terms are positive. And you're just adding more and more terms. Okay, so what we have got is, this is our definition. And so remember, the first term is, although I'm writing it as 1, you can also write this 1 by 0 factorial to fit the pattern. Okay, so this is E, and we'll take this as the definition and this series as its value. Now we'd like to define a function using this called the exponential function. Okay. So this is defined as e to the power of x, or if you want, f of x equals e to the power of x. So for each value of x, you get some e to the power x. This is just normal exponentiation. So you take the value of e and raise it to the power of x. So for example, f of 0 is what? E to the power of 0, which is just 1. Anything non-zero to the power of 0 is 1. So e to the power of 0 is 1. And f of 1 is e to the power of 1, which is e. Anything to the power of 1 is itself, right? So this f of 0 is going to be exactly this value again. But you can also find, for example, f of 2, which is e square. And to find the value, you don't need the series. If you know the value of e, you can find the value of e square also. So let me quickly find that. Just a minute. So I'll find this value, and also you can find f of minus 1, which is e to the minus 1, which is 1 by e, right? So let me find these values. Right. So this is approximately 7.389, and f of minus 1, that is 1 upon e, is approximately 0.367. Okay, these you don't need these values. I'm just showing you that it's possible to find all these values. Okay, so from this function, so these will give you different values. However, you can also evaluate these in some other way. So if you consider this as a function, according to this definition, e is this limit. Okay, e is this limit. So e to the power of x will be what? This limit to the power of x. Now there is a property of limits which states that if you have a limit to the power of x, and if that limit is itself defined as in it has a value, so which it does in this case, then you can also take this x inside the limit. So instead of finding the limit and then raising it to the power of x, you can also take the expression which you are evaluating, okay, and raise it to the power of x, then find its limit, and these should be equal. But here what you have something of the form a to the power of b to the power of c. And what is that equal to? A to the power of bc. So over here, this is a to the power of b to the power of c, which is a to the power of bc. Okay. So this becomes this new limit, which we need to evaluate. So how to evaluate this? What we did previously in this case, we did the binomial expansion. We expanded this binomially. So the same thing can be done here. So this limit 1 plus 1 by n to the power nx can be expanded in the same manner, only now the exponent is nx, not nx. So you'll get over here you get summation k equals 0 to infinity nx ck times 1 upon n to the power of k. So if you ask what is nx upon k, nx, this x need not be an integer. So although I said you can find f of 1, 2 and so on, you can also find f of 1.5. So you can find, for example, e to the power 1.5 or e to the power 0.5, right, e to the power 1 by 2 and all those. So this x need not be an integer, so nx need not be an integer, but that doesn't matter. You can still write this nx ck in the same way as nx times nx minus 1 times nx minus k plus 1 upon k factorial. And then again do the same thing, cancel the n and so on. So I'm not going to do this in detail. I'll tell you the final answer, but I hope you can see the logic where this is going. You have still, as before, k different brackets with n in them, but now you also have x in them, right? So what you will be doing is taking out all these nx terms. So this becomes nx to the power k, because from k brackets you're taking them, and then the remaining thing becomes 1 times 1 minus 1 upon nx times 1 minus 2 upon nx and so on. Okay, minus k minus 1 upon nx, and then there is a k factorial here, so that, and this is 1 by n upon k. So here you'll have 1 by n upon k. I'm sorry, n to the k. And so this nx to the k is n to the k x to the k, and this cancels out. All of these become 1. So each bracket becomes 1, so the product also becomes 1. So all you're left with is x to the k and k factorial. So earlier what we got was the kth term would be 1 upon k factorial, right? But now it will be x to the k upon k factorial. So if I just write the final answer here, I don't want to do the whole derivation. So if I just write the final answer, what we get is e to the x is summation k equals 0 to infinity x to the k upon k factorial. Okay, or if you expand it, so k equal to 0, you have x to the 0 upon 0 factorial. So that's x to the 0 is 1, 0 factorial is also 1. And the second term will be x to the 1 upon 1 factorial. So that is x upon 1 factorial plus sorry, plus x square upon 2 factorial, x cube upon 3 factorial, and so on. Exactly in this form for different values of k. So this is e to the power of x. So you have to take this as a result that you need to remember. E to the power of x is this series. So even if you don't understand the derivation completely right now, that's okay. But please remember the result. E to the power of x is given by this. So we have defined e to the power of x as a function using e and raising it to the power of x, but it also has a different expression in terms of an infinite series. This is a so-called power series. Power series because each term has a power of x in it with some constant. So this is called a power series in general. This particular power series is the series corresponding to the function e to the power of x. So if you in this, if you set x equal to 1, what will you get? You will get e power 1, right? If you put x equal to 1 here, you get e to the power of 1, which is e. And over here, what will you get when you set x equal to 1? You should get the same thing. But what do you get? 1 plus x becomes 1 by 1 factorial. X square upon 2 factorial becomes 1 square, which is still 1, upon 2 factorial. Then 1 upon 3 factorial, and so on, which is exactly our initial definition of e, or the initial series that we got for e. This series is exactly what we get if you put x equal to 1 in this general function, right? So this is more general than what we obtained before, because here you can find e using a particular value of x, and right, what happens if you put x equal to 0 here? So here also you're putting x equal to 0. So this term remains as 1, but this becomes 0, 0, and so on. So you'll get e power 0 is equal to 1, which is again as expected. But you can also now evaluate new things which you could not have done from this definition, right? For example, you can evaluate e to the power of minus 1. So if you find you want to find e to the power of minus 1, that is 1 upon e. Anything to the power of minus 1 is the reciprocal. So e to the power of minus 1, according to this series, what is it? Well, the first term will be 1, right? This will become 1. And what about x by 1 factorial? X is minus 1. So 1 plus minus 1 upon minus 1 upon 1 factorial, which is 1 minus 1 upon 1 factorial. What is the second term? Minus 1 square upon 2 factorial. So that is plus 1 upon 2 factorial. Third term is minus 1 cube upon 3 factorial. Minus 1 cube is minus 1. So this will be minus 1 upon 3 factorial, and so on. So this is also a very similar series. The only difference is here the sign is alternating, right? It starts with plus 1, then minus, plus, minus, and so on. So e to the minus 1 is a series that looks almost like the series for e, but with alternating sign. Okay. And then, of course, you can find e to the power of 2 and so on, but those are obvious from this. Nothing interesting there. E to the power minus 1 is particularly interesting because almost the same thing, only with alternating sign. Okay. So these you need to remember. At least e to the power of x in general you need to remember. Is it fine so far, or any questions about this? E to the power 0 is equal to 1 from this one. Right? You put, I mean, in general, we know that if you take any non-zero to the power of 0, you always get 1. So you can also see that from this series. If you set x equal to 0, this becomes 0. All of these become 0, except for this, which remains 1. So you're getting 1 plus 0, etc., which is 1. Okay. Any questions? Okay, so then now remember that we discussed trigonometry and defined the sine, cos, tan, etc. functions. So in order to do calculus with that, we cannot use a triangle definition because that's geometry, right? You just have a geometric definition there. You have no way of evaluating the sine function, for example, at different values, other than actually drawing a right triangle and then with the correct sides and then measuring that ratio, adjacent by hypotenuse, opposite by hypotenuse, and so on. Right? So that definition cannot be used in theory, at least for calculations. So what we'll do is we have Euler's theorem, okay, which tells us that there is a relation between the exponential function and the trigonometric function. So Euler's theorem tells us that if you take the exponential function e to the power of x, which we just defined, and compute e to the power of ix, where I is the square root of -1, the imaginary, so-called imaginary square root of -1, then this is cos x plus I sin x. Okay, this is Euler's theorem. How can we use this to obtain expressions for cos x and sin x in terms of the exponential function? The exponential function is something we already know. We know a series expansion for it. So this tells us e to the power of ix in terms of cos x and sin x, namely this. But we want it the other way. We want to get expressions for cos x and sin x in terms of this. So let's see what happens if you. So what we know is, if I take this directly, we have e to the ix is equal to cos x plus I sin x. Okay. What about e to the minus ix? What will this be? So here you have e to the minus ix, which is e to the power of I times minus x, correct? Now this x is variable. It can be anything. So if I put x equal to 0 here, what will I get? E to the power of I times 0. That's e to the power of 0. And over here I'll get cos 0 plus I sin 0. And as you know, cos 0 is 1, I sin 0, sin 0 is 0. So this will become, give me, for example, I'm just giving an example. E to the power of I times 0 is cos 0 plus I sin 0, which is 1 plus I times 0, which is 1. Okay, similarly, if you put x is equal to, let's say, pi by 2. Okay, so as another example, e to the power of I times pi by 2 is equal to cos of pi by 2. Okay, pi by 2 is 90, remember, pi by 2 radians is 90 degrees. So cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0. I sin pi by 2 is 1. So it is 0 plus 1 I, which is I. And so on. you can evaluate this at any real value of x, or any value of x actually, right? Any value of x you can substitute here and you will get the corresponding value here. So we want to find out what is e to the power of minus ix, but minus ix can be written as I times minus x, just ordinary multiplication and signs. Okay. So if you use this, you compare this and this, in place of x there is minus x. So here also in place of x we'll have to write minus x. So this becomes cos of minus x plus I sine minus x. Remember, cos is an even function. So cos of minus x, or if you prefer the other notation, cos of minus theta is cos theta. So this will be cos of positive x itself. However, what is sine of minus x? Sine of minus theta is minus sine theta, right? So this is minus sine x. Now, please remember to write the brackets here when you're writing this. It is not I minus sine x, it is I times minus sine x. So what do we get here? E to the minus ix is cos of x plus I times minus sine x, or in other words, minus I sine x. So this is clear, right? I'll erase this. Hope you understood how we got that. Okay. So we have these two expressions. Let's say equations 1 and 2. Again, what we need now is the value of cos x and sin x separately. So what happens if you add the two equations? On this side you get e to the ix plus e to the minus ix. And on this side, when you add the two right hand sides, what do you get? Cos x plus cos x. So 2 cos x. I sin x plus minus I sin x, that's 0. So we get 2 cos x is equal to this, or in other words, this implies that cos x is equal to e to the ix plus e to the minus ix by 2. Okay. So this can be taken as a definition of cos x, or an expression for cos x in terms of the exponential function. In the same way, can you get sin x? From these two equations, how do you find the value of sin x? So if you do, I hope you found the answer, okay? Even if you're not answering it, I hope you found the answer by yourself. What you need to do is subtract. I mean, one thing you can do is take this cos x expression and substitute it here. So that's just going to be a tedious calculation, slightly. Instead, you can very easily subtract second equation from the first equation. Then you get e to the ix minus e to the minus ix. That's going to be this minus this. So cos x minus cos x 0, because you're subtracting now, and I sin x minus minus I sin x, minus of minus plus. So I sin x plus I sin x is 2i sine x, right? So again, this implies that sine x, we want sine x, not I sine x. So sine x is e to the ix minus e to the minus ix upon 2. All right. These are the two expressions. I mean, these are the, oh, sorry, yeah, correct, correct. 2i, not 2, 2i. Forgot that. Yeah, so these are the expressions for cos x and sin x in terms of the exponential function. This allows us to calculate, theoretically calculate um, facts about cos x and sin x. For example, you can now find limits involving cos x and sin x because you know it in terms of e, and e itself, or e to the power of x itself, is known in terms of its series. Okay, so from these two we can also get series expansions for cos x and sin x. So I think we have 10 minutes left, so we'll find the series expansion of cos x, and similarly you can by yourself find the expansion of sin x, series expansion of sin x. So to find the series expansion of cos x, we just use this expression. But let's look at this. You have e to the ix plus e to the minus ix by 2. So first of all, similar to how we found over here, we found e to the power of x expansion, right? And from that we found e to the 1 and e to the minus 1. So in general, we can replace x by any other variable like minus x or ix or minus ix and find expansions for those. So the first thing we'll do here now is we'll find an expansion for e to the power of ix. Okay, let me first write down the general expansion for e power x to remind you. E power x is 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial and so on. So using this, e to the power of ix should be 1 plus ix upon 1 factorial. You just replace x by ix everywhere. That's what is happening. Here x is replaced by ix, right? So just replace x by ix everywhere in this. Now, okay, I'll write this step first and then simplify. Ix the whole square by 2 factorial. Actually, we'll need more terms to see the pattern. So ix cube by 3 factorial, and the next term will be ix to the 4 upon 4 factorial and ix to the 5 upon 5 factorial and so on. I'm just writing more terms so you can see the pattern more clearly in the next step. This is 1, no problem. This is ix, also no problem there. What is ix square? So ix square is I square x square. But remember, I is the square root of minus 1. That's our definition of I. So I square is minus 1. So this will be minus x square. So here you will have not plus, but rather minus x square upon 2 factorial. I is not there. Okay. I square is minus 1. So there's no I term in this. It's just x square upon 2 factorial. Over here, what happens? Have ix cube is I cube x cube. What is I cube? I square itself is minus 1. So I cube is further multiplication of that by I, which is minus I. So here you will have minus I x cube upon 3 factorial. Similarly, here you have ix to the 4 upon 4 factorial. I to the 4 is I square the whole square. I square is itself minus 1. Minus 1 the whole square is plus 1. So you'll get plus here, plus 1 here, and x to the 4 upon 4 factorial. And then next, so actually if you look at the pattern, or if you look at the terms, you can see that you don't need to find I to the power of 4, I to the power of 5, etc. You can just take the previous term. What is the difference between this term and this term in the numerator? What is the difference? You just have to multiply one more ix, right? So if you take this and multiply one more ix, what do you get? Plus I x to the 5 upon 5 factorial. Denominator you can already see, right? So each term you just multiply an ix in the numerator, and that is the next numerator. So 1 times ix. Ix term times ix is minus x square, because I square is minus 1. Further multiplication of this by ix will give you minus ix cube. Further multiplication of that will give you minus I times I is minus of minus 1, that's plus 1, x to the power 4, then ix to the power 5, and so on. All right. So this should be somewhat clear. Okay. So here you can see it's not exactly an alternating series. Alternating means the signs don't alternate every other term. Right? Every other term does not have a different sign. You have two terms with the same sign. Both of these are plus. Then two terms with the other sign negative. Again, two terms with positive sign. And next will be actually minus. Here this will be minus, and so on. Okay. And what does alternate is the presence of I. The first term has no I in it. Second term has I. Third term does not have I because it's an even power term. So an even power of I is always going to be a real number. And an odd power of I is always going to be I itself with plus or minus sign, but it will always have I in it. Right? So this presence and absence of I alternates, and the sign alternates for two terms, every two terms. This is e to the ix. We also need e to the minus ix, but that's not difficult because if you replace x, by minus x, ix becomes minus ix. So we already have the expansion of e to the ix. So in this, you don't need to calculate everything from the beginning. Just replace x by minus x in this final expression. Okay. So here you have 1. Here x becomes minus x. So you get 1 minus ix upon 1 factorial. Here x becomes minus x, but minus x the whole square is also x squared. So this sign does not change. This is minus. This will be x square will become or will remain x square. So you just have x square itself. What happens here? Again, minus I is there. That does not change. But x cube will be minus x the whole cube. Minus x the whole cube is minus of x cube. So there will be an additional minus here. So this will become plus. Again, denominators are not affected. Here x to the 4 becomes minus of x to the 4, which is also x to the 4. Similarly, here you will get again a change of sign. So all the odd power terms, the signs will change, and the even power terms, the signs will remain. Right? So this is also a series where the sign changes every two terms. The first term has positive, next two terms have minus, next two terms are positive again, and so on. And I will again alternate between every term. So you have both of these now. So you have now e to the ix as well as e to the minus ix. Now, if you look at the expression, cos x is the sum of these two divided by 2. Okay. So if you add these two, then we'll divide by 2. So first let's just add them. This is these two, you're adding these two. Okay. So 1 plus 1, 2. Ix by 1 factorial plus minus ix by 1 factorial, that's 0. So that term is gone. Okay. Here you have minus x square by 2 factorial, again minus x square by 2 factorial. So minus 2, I'll not cancel the 2 in the denominator, I'll keep it as it is. Minus of 2 times x square, or let me write it this way. Minus of x square by 2 factorial times 2 because both of these. And over here again minus and plus, but everything else is the same. So this minus and plus cancel. So that next is also 0. Here you have again x to the 4 by 4 factorial added to itself, so times 2. Next term will again cancel out and so on. So every term has a 2 in it, right? Because every term has become double of what it was, except for the first, the second, fourth term and so on, which have become 0. So this is equal to twice 1 first term. 2 I have taken out, so 1. 0 is there, ignore it. Second is minus x square upon 2 factorial, because again this 2 is taken out. Third is 0, ignore it. Fourth is again 2 have taken out. So what remains is x to the 4 by 4 factorial. Now you can guess the next term will be x to the 6 upon 6 factorial, because again you can see this cancelled out, right? So the next term will be x power 6 upon 6 factorial. Wait, this should be minus, right? Because you can see the sign will alternate. And then x to the 8 upon 8 factorial with a plus sign, then minus, and so on. Right? So this is e to the ix plus e to the minus ix is twice of this. So if you divide by 2, e to the ix plus e to the minus ix divided by 2 by taking 2 to the other side. This is 1 minus x square by 2 factorial plus x to the 4 factorial, 4 by 4 factorial minus x to the 6 by 6 factorial, and so on, right? And this was our expression for cos x. So cos x is given by this series. This is an alternating series. Unlike this earlier one, this is an alternating series where you have plus, minus, and so on. But all the terms have even power of x. So x square, x to the 4, x power 0 the first term, x square, x4, x6, and the denominator is the same thing with the factorial. So x square by 2 factorial, x to the 4 by 4 factorial, and so on. The series is very simple in pattern, easy to remember. So this is the series for cos x. So I'll stop now. For the next time, please find the series for sin x. Okay. Find the corresponding series expansion for sin x in a similar way by using this definition. So you already have most of the work done here, because e to the ix and e to the minus ix is there. So you just need to subtract them and carefully cancel out the terms and write the remaining terms. So you'll get a series for sin x. Okay, we'll stop for now. Do you have any questions? Okay, I've tried to record this, so hopefully I'll be able to send you the recording or upload it somewhere if that is recorded properly. And I'll send you this notebook also, which on which I've written. Thank you.